All right, so today my plan is to talk about integration. So if you're a student who is preparing for NEET or you're a student preparing for JEE and you're in class 11th, this concept will come in handy in many numericals in physics. Now this could be simple type of integration and some complicated methods like substitution. What I'm going to talk about integration today is the fundamentals of integrations. So just watch my video carefully, and I'm going to pick up a daily life analogy to explain you what integration is. Okay, so we will keep it very simple so that you can understand integration as coming from your daily life. So just concentrate on the video. All right, so let's talk about integration, okay? Now, I'm talking about something very, very fundamental here. So let's talk about, a bucket, okay? So that's your bucket. And, obviously, bucket has to be filled up with a fluid. Let's talk about, water. So what you have is a situation where you have a tap and, the tap has water coming in and filling up this bucket. So we're talking about bucket, and what I'm explaining you is the concept of integration. Okay, don't lose sight of the fact that what I'm telling you is integration. So that's your bucket, and that gets filled up with the help of this tap, and this water is coming in. And all right, so initially, this bucket, before the water started filling this up, has a volume V0, okay? So that's a volume when the water is not coming down, okay? So that's your initial volume of, water, which is available in the bucket. And now you open the bucket, open the tap, I'm sorry, and what you do is now water, starts pouring in, and that's your water, which is pouring in, okay? Now, you can control the tap. So the water was filled up till this place. And once you, open the tap, this is what happens, right? So the water cup keeps on coming down, and the level of water starts going up. Now, the rate at which the water is filling up this bucket, can be said to be maybe some rate dr by, maybe something, this is the volume of water which is coming in, and, every second, it is getting filled up. So this is the rate, initial rate, maybe some rate, God knows what it is. Maybe it was some, volume or centimeter cubes per second, and so water was getting filled up. And then what you did was, you opened the tap further, okay? So you opened the tap further, and therefore the water that started coming in, is at higher rate, okay? So the rate at which the water is flowing in, maybe this was, some value X, and now the rate of flow of water, inside the bucket, it has become, maybe, Y centimeter cube per second. So the rate is changing, okay, the rate of flow of water. And therefore, in a small time interval, the bucket will have a volume which will be the initial volume when there was no water coming in from the tap. So initial volume plus a very small, volume will get added to it because of this rate, right? So if the time dt has elapsed, so the volume which will get filled up is this much, okay? So the volume becomes V0 plus dr, okay? Or you could, write this as V0 plus x dt, right? Because dr is equal to x into dt. So this is a new volume which has got added to the bucket.
And now what you're doing is you are further filling this up, because you have, opened the tap a bit more, and more water in the same amount of time has got filled up. So initially, if it was just, some water which got added, this time more water is getting added to this, right? So now your new water, is, you already are at V0 plus X dt. And this time your rate has increased. So in the small time interval, the additional volume of water you have added, a very small volume, is y dt, right? So now your new volume is this. This is after another time interval dt, okay? And similarly, you can, increase or decrease the rate of change of, water flow and keep on increasing the water. So this is the water after time interval dt, and this is the water level after the time interval 2 dt. And this is where we started off, okay? Now, if you were to look into integration, integration also deals with something like this. So what it does is, if you have something like, so if I were to represent this small volume change, I would show that at a very small time interval, the amount of water which has got added is x dt, right? So that's the water level which increases with time. So you could see that the water which has got added is only x dt, okay? And then, after dt seconds, some more water is getting added. And maybe this time, the water level is increasing to, in the same time interval, the water which is getting added is, y into dt. So this is what's happening, every dt second maybe, now somebody comes up and says, I'm going to open some more water so that in a small time dt, more water comes in. So in the same time interval, you will have more volume, change being observed. So this is more water coming in, in the third dt second. It's a very small time interval. And then someone comes and says, this is like too much water coming in, and I want to slow down the rate at which the water flows. And therefore, this gentleman comes and, slows down the water speed. And in this time interval, the water that comes in is just z dt, because, your rate of flow, which I said is dr by dt. This time your rate was just z, okay? So one is your rate, this is a rate, and this is a rate, okay? And this was also a rate. So the rate keeps on changing, okay? And the actual volume, which is this, also in the same time interval keeps on changing. So if you were to plot a graph, which shows, for example, the rate versus the time, what you find is if in a small time interval, the first rate is, this rate, which is x, you could show it maybe here, and then it increases to some value, which is this, which is, y, and then, it becomes z. Maybe this time the rate goes up in the same time interval drastically up. The time interval elapsed is same, but the rate has gone up from y to z. And then, maybe it fell down in the time interval dt. So all these time intervals, are dt time intervals, okay? So this is also dt. Don't worry about the size. This is dt. And you could have one more change. This is again an increase. And this is also for all, dt. And then the rate comes down. So this is your rate, and the rate is going down. So this is your rate versus time graph. And if you connect the dots, what you find is this, okay? That the graph looks like this. And when you integrate this, which means you try to find out, how much water is getting added, in this time interval, which is, dv which I'm writing as actually dr, we can change it to dv. So this is a small change in volume, right? So this is a small change in volume, and this is also a small change in volume. So small little volumes are getting added in every time, interval. So one is a rate versus time, which could be, rate could be acceleration, which is, dv by dt. And when you integrate, what you find is that in every small time interval dt, how much is the change in velocity. So your dv comes out to be a dt, and then you integrate, what you get is the change in velocity. So in our case, we are integrating the small volume, which is this and this and this. So essentially this graph, the small volumes you see is nothing but the area under the rate versus time graph. So, if you know the rate of change of a physical quantity with respect to another physical quantity, you can actually find out the change in that physical quantity. So in this case, the volume was changing with time, and we can exactly find out how much volume actually gets added by the concept of area under the graph. So what I'm showing you are small areas, is nothing but these areas. So when you integrate, essentially what you're doing is you are integrating the rate of flow of liquid, which are represented by maybe dr by dt, or you could say small change in volume every second of time. If you integrate this, with respect to time, what you will get is small areas, and this area under the curve will tell you that in every small time dt, how much water got added. So if this area gets extended like this, because the rate is continuously changing. So the rate here is this much, the rate here is this much. So the rate keeps on changing, right? And therefore, if you see this rate is very high. So corresponding to this, the amount of water which got added, is very high, okay? So the water is this much. So the small areas you see is nothing but this area under the curve. So essentially, the rate versus time, would give you the actual volume that changes in this particular case. When you keep the water coming in this bucket from maybe time t is equal to 0 to t is equal to 10 seconds, and you continuously change your rate of volume, and this is your rate of change of volume, maybe with time as square of time, and then you want to find out what is the change in volume that took place. So you write dv by dt is equal to t square, and dv is equal to t squared dt, and then you integrate and you integrate. You want to find the change in volume from 0 to 10 seconds. So this is what you get. And if you integrate, you get it as t cubed by 3, and you can write it as 0 to 10. So this will tell you the total change in volume of water, which happened from 0 to 10 seconds. So, and this is nothing but the area under the curve. So you must understand that integration as an exercise, what does it mean conceptually? That's a first step you have to understand. And what I'm doing is, this is, maths for, physics series, and you can watch a lot of videos which I prepared on my YouTube channel. There are around 1,400 videos pertaining to physics. And this is an example where, when you are entering your class 11th and you're trying to understand, and then you're a NEET student, who doesn't know what is integration. You can use this example to understand the meaning of the word integration and the concept of area under the curve. Just use water coming in from a tap and, filling the bucket and, with different varying rates, and the bucket is getting filled up in small time intervals with different quantities. And all these quantities finally tell you what is the final level of the bucket, after 10 seconds, okay? So this is a way you use integration in a lot of numericals in physics. And my suggestion to NEET student is you don't need to learn very complicated integration, but for JEE students, they would need to learn advanced formats of integration. So I hope you loved this video and you liked it. If you did, please subscribe to my channel and give me a thumbs up and a feedback on the topics you would like videos on, so that I can be of some help to you in your NEET and JEE and board examination. So thank you very much for your attention. And it was my pleasure, sharing my knowledge with you. Thank you.